So specifically for Sixtrack part, I continue with the introduction of Sixtrack. We use it as an example for what needs to happen to Fortran code. And you've heard from Dimitri what kind of techniques they developed to master the specific Fortran issues they found in Sixtrack. Now, for the next step, just a few words about what we want to get with Sixtrack ourselves. This is actually a slide on statistics from users, actually volunteers. Users are certain stuff. Volunteers who actually run our code out there on their PCs. This is a timeline for the last 60 days, and this is number of users, volunteers, who are actually, it's supposed to come back, who are actually executing the code. Yeah? It's what? We need to get room selected, so room PC, laptop, HDMI. Hopefully it will come back. Yeah, okay, that's good. I probably slips from time to time. So altogether, we have actually, the number of users is actually quite large. It's like 130,000. But actual active users are only like 7% who really execute the code. This is nothing we can do about right now, but it's a curiosity slide for us, just also giving you the impression that we do command quite a potential in possibilities to execute out there. No? So why does it sleep all the time? No, it is actually on the net. And here? So? Yeah. The next slide is maybe more interesting. This is the actual hosts, the computers which people give us for this work. On average, there is about 50% more CPUs than users in this in the community, and this is the distribution of the resources. You see that actually most of them are Windows, and with respect to last year, maybe another curiosity fact, the Linux community grew by a factor of 2. We used to have 12% Linux last year, now it's 24% Linux. But then still, among those, it looks like most of them are Windows 7, Windows 8 to some extent, mostly Windows 7, and that means that the majority of the machines are actually newer machines with most likely modern CPUs and GPUs in particular, which give us an opportunity to exploit them, because right now we do not use those GPUs out there at all, right? So apparently there is huge potential for unused cycles out there for computation for Sixtrack. Now, just going to another example of Milky Way at home, which is another project for the volunteers. They have ported their software to usage of GPUs a few years ago. Of course, so they have to distinguish out there with handle different hardware. Is it Nvidia? Is it AMD? What kind of combinations? Overall, this increases substantially the load on the team who develops software. Like 16 versions of executables are provided by Milky Way at home team to satisfy all different hardwares out there. For us, we provide probably about 6 different versions just to take care of all the CPUs and 64-bit, 32-bit, all that. But this is way to go to be able to tap into this potential, but the potential is huge. Right now, Milky Way actually 140 times more efficient in extracting cycles from from this community as we are with Sixtrack. So this is where we can go and actually increase our possibilities to utilize the cycles out there. That's the motivation for the Sixtrack team to actually port and use the GPUs. And with that, maybe I can give it back to Dimitri to give the final part of how to specifically use the techniques for the Sixtrack.
Okay, so in fact, we already discussed a bit of technical details. This meaning that this part will be a little bit shorter, and we will also explore the current state of the code. So. So what things are important for us from the software point of view about Sixtrack? So we have a single-threaded code, which will have, as I explained, we have to transform to multi-threaded thread-safe code. Also, we have a strict requirement on numerical accuracy, meaning that Sixtrack provides its own mathematical libraries for, let's say, for instance, to compute trigonometry, and in order to conserve this accuracy also on GPU, we basically need to conserve the same approach with software math library also on GPU. So we have command blocks that we transformed into models. We have a very deep call graph, meaning that any handmade effort of porting this on GPU would be a job of 4 months. So our goal is to automate as much as possible and conserve the results of correctness tests. We have a lot of small loops. These small loops by themselves are not enough to utilize the compute power produced by GPU. We need multiple instances of small loops. Actually thousands of instances of small loops, which is in our case delivered by ensemble simulations. We have diagnostic output and file I/O intermixed with computations, which has to be handled somehow, as long as we want to provide to developers the same level of comfort for GPU level as they already have for traditional CPU version. Well, and actually, even the most important point missing from this list is that we want to keep a single code base. So as Igor showed us, I'm just touching the table and it disappears. Okay, I'll stay away. So we would like to keep a single code base as much as possible. As Igor mentioned, there could be 19 or 6 or this kind of ranges of version that have to be maintained. We aim to provide a version that will be still consistent for CPU compilation. So as I'll show you in our code base, we maintain the source in a way that it will compile binaries that are both capable for CPU and for GPU. We believe that this conservation, this elimination of source segmentation is very important for conserving the development resources. Okay, so on GPU we have specific numerical problems. For example, numerical reproducibility could be limited by the usage of FMA4 instruction. So FMA is well, actually not 4. DFMA, double precision FMA, DFMA, is floating multiply add, fused multiply add, meaning that addition and multiply operations are performed as a single operation on the assembly level. Unfortunately, for some additional performance, the price is the loss of accuracy. Or actually, this is not the loss of accuracy by itself. It's the change of reordering of operations, basically. So on this reordering of operations may introduce problems with numerical reproducibility. So what we had to do is to find the switch in Nvidia NVCC compiler and disable FMA instruction generation. So software math library for Sixtrack is implemented in CR-libm. Well, the funny thing is that if you develop a GPU kernel utilizing double precision sinus or cosinus, for instance, and then if you dump the assembly, you will see that these functions are also implemented in software. They don't exist just in a single instruction like cosine, call cosine, and nothing more. They are from what we have on GPU by default. Math, this kind of math, especially double precision, is also in software, which means that by bringing Sixtrack's CR-libm onto GPU, we are doing something natural in terms of what is already happening on GPU. So instead of their built-in math library, we are providing our own math library, and the difference in performance is minimal. But we still have to study some tweaks from built-in GPU math library. For instance, there is so-called constant memory, specially dedicated cached read-only memory in read-only memory partition on GPU, which in case of built-in trigonometry used for storing these tables of magic numbers. So in case of Sixtrack, we also have these tables of magic numbers, and what we can learn from built-in functions is that we should also map these tables onto constant memory. And for the rest of the things, the code could be the same. Yeah, I'll show, I guess, the example a bit later. Well, if we are handling a large code base, please expect problems with compilers. Unfortunately, this is the real life. For instance, compilers from some vendors tend to hang on large Fortran files with specific levels of optimization. It's a known problem. And in case of PGI CUDA Fortran, we are more vulnerable to the problem of compiler crashes. In case of this multiple thousand lines of codes in a single source file, well, this is a question of compiler quality and also the question of about their test suite. Anyway, we have to provide a workaround, and our workaround is to split one subroutine per compilation unit. So original code from Sixtrack came to us in maybe 4 or 5 very large Fortran sources. What we had to do is to decompose it into, let's say, into several hundred small files with individual subroutines. Moreover, these subroutines are required to live in models. So this is the rule of CUDA Fortran. Any kernel, any device function. Device function is a function called from GPU kernel. Has to be defined inside of model. So we split large files into small files, each one for individual subroutine, and every of this subroutine has an artificial model around it. So just to maintain the required rules. This is number 3 is also the problem with compiler we faced. Interestingly, Fortran compiler by itself generates an intermediate sources that cannot be compiled any further. So it directs itself into impossible state or something like this. So it cannot continue compilation from some intermediate state. So we still had to get underneath and do a fix. The really nasty thing is absence of function pointer support. That's another thing missing from CUDA Fortran. There are several places in Sixtrack code where something is done with function pointers. So fortunately, it's not a recursion or something really impossible to be done in other ways. So we have to get rid of these function pointers where it's possible. Or another way would be to rewrite some portions in C in CUDA C. Fortunately, in CUDA C++, we have function pointers. Okay, so and this is to give you an idea of what we are doing in our compiler in order to remember, provide this if conditions for threads filtering for serial code. So this is the idea is simple. We know the pipeline of Fortran code compilation. So as in any compiler, it could be decomposed in several stages: backend, middle end, and front end, middle end, and backend. So from the left to the right, Fortran frontend, then CUDA-C optionally, then a middle end LLVM-IR, then backend is PDX and Qubin. So this CUDA-C is actually it's embraces because in newer version of CUDA Fortran it's not used anymore. So in earlier time, when we started this Sixtrack project, CUDA Fortran was first converted into CUDA-C, and then CUDA-C with Nvidia mainline compiler was transformed to PDX assembly. And now in modern versions, they have CUDA Fortran generating assembly on the fly without this intermediate C representation. Well, for us it doesn't matter. The thing that matters for us is that we somehow have to intercept this pipeline somewhere in the middle end. So having access to the final assembly is not enough for us, because we want to modify something in the code before generating the final assembly. So remember, we want to introduce these if conditions. And the way to do it is actually to grab this LLVM-IR representation, which is called model. So model is like an entity corresponding to a source file or to an object file. So model will end up as an object file. So Nvidia CUDA compiler by itself is closed source. Nobody allows us to reverse engineer it, so it's illegal. So what the only thing that we can do is just to analyze things that it's using from open source, from LLVM. So we use a very simple heuristic to pick up the point of interest. So we have our compiler executable running, and we track memory allocations that it's doing. So well, we basically re-implement the built-in malloc with our own malloc, and then we inside this re-implemented malloc we check the size of allocation, if it's corresponding to the size of model type, and well, actually we have some additional if conditions here for more precise capture. Then when we think that we have the pointer to the model object that will be later populated by this intermediate representation, and at some later time steps, so we captured the pointer, but we still don't have the actual data inside of it. It was just allocated, and then this local time hook is a point where we expect this model to be populated with the actual representation. So when we capture the model, then we can simply modify it using LLVM tools. So this representation of model is essentially it represents the code as a collection of functions. Then each function is a collection of basic blocks. Basic blocks is a collection of instructions. Then we can dig further and further and find the instructions for calls. Then find the calls corresponding to these pairs we have here, and then just to arrange everything to have these things stripped, and to have the negation, the rest of the code to be an if condition. So this is the basic idea. And maybe to show you how it looks like, well, I was afraid that I'm given an impression that we've done something terrible or very, very complicated, and you will be no longer able to use this code. Just in case if this is the case. So this is how our code base looks like. So we still maintain the Fortran version as one of the targets. We have PGI Fortran ACC. Well, but it's inefficient, so it's not going to production. And we have PGI CUDA Fortran. So in every of this branches, we have what I already warned you about, that we have separate sources for every subroutine. Every subroutine is now has an annotation like attribute device and attribute global, meaning that as I told you, we would like to maintain both CPU and GPU version in a single source. So it could be so from this every single source file, we will generate a device function for GPU and also a host function for CPU. So the rest of the code stays unchanged, except of common blocks. So you see, instead of common blocks, we now have models. So everything what we had in common blocks is now models. And this thing is also introduced by us we also introduced explicit interfaces. No, actually, this is the model. So this is how it looks like instead of common blocks. So it's a little bit verbose, but Fortran by itself is verbose, right? So in terms of code state, I think it's still in very good position. We just have this bind C alternative names here, and for each data instance inside of model, we provide its mirror in GPU memory, which shall go with attributes device. For CUDA Fortran, that means that these particular variables will be in GPU device memory, not on host. Okay, and I'm not sure if the control outputs are here with me. They should be. No. Not really. Anyway, so just to explain you a bit more about our methodology, we are doing things refactoring step by step. So for every step, we analyze the whole suite of Sixdesk for results correctness. So we check that the same outputs are produced for every modification we do with the code. And the state for the GPU version we approach so far is that we have all the code on GPU, and we have to organize that annotations. So we need, let's say, a bit more working hours to decide what loops are safe to be treated as parallel. So these directives are still to be set manually. So this is the only thing we have to do manually. As you see, we got rid of a lot of useless technical refactoring jobs. They are now done automatically, but these things have to be done by developer. So this thing is just one remaining item we still have to focus on, and we would really appreciate the feedback about the usability of our approach. How do you feel if it's comfortable for you to extend this code representation? If it's comfortable to maintain and handle it on a daily basis. Yeah. So this is what I would like to leave for discussion.
Okay, maybe I have already some question and comments. So let's say starting from the source code. So typically in Sixtrack we have let's say our original source code is in these .s files that are
exactly
assembled. Let's say they go in two pre-processing stages.
Yes.
And then they make some Fortran code. So yeah, exactly. So there, I think to have something workable, we will need to introduce all your let's say modification, even if they're small, into this source code. Unless you have a way to automatically introduce notation directly from the Fortran code that is generated.
Okay.
So also the splitting, I think if you need split file, then we should find a way to
perform the split from this exact representation.
Yeah. Yeah. So this could be done. It's some work, I would say. I mean, the information is there. So this pre-processing, so there are two stages. So one is to assemble code blocks. If you want, is a poor man inlining of functions at the end. And then there is another one that is more complicated, which is it's basically turning expressions in atomic functions that use a particular library to perform, let's say some algebraic computation on polynomials. So basically, you will see in the code that there are some expressions with this. If you look for Fox in the .s, capital Fox look in Sixtrack.s. Yeah. Capital Fox. Yeah. If you look for it. Yeah, exactly. So these are expressions that basically are compiled in atomic. It's like basically there is a kind of register-based virtual machine that that is put in place. So somehow this was again as a poor man to do operating overloading. This was done 20 years ago. It's basically a replacement of operator overloading. So it's something done 20 years ago, but this is a kind of implementation of operating overloading for a certain type of calculation that we do with polynomials instead of real numbers. So if you see, let's say, the translation of this portion of code in Fortran, you will see a set of add, multiply, and so on. So also that could be done. Could be interleaved with your annotation, but of course this needs to be somehow managed. It's also true that this part is performed only once at the beginning of the computation. So if you want, it's part of some pre-processing before going in the computation-heavy loops. So I don't know if this part could be managed on the CPU side and only and somehow produce a state that can be then transferred by to the GPU. But also I see that it defeats a bit the purpose to have a complete, if you want, Sixtrack instance in the GPU, that I see as a strong advantage, because it basically avoids you to think about many details like that. So I don't know, I see that there is at least the approach of translating the Fortran file and do your manipulation is fine.
Okay.
But one has to solve the problem of, let's say, doing this pre-processing step. Of course, when we develop, we change this .s file. So it also will be very difficult to do, let's say, this splitting manually every time we have to change.
Yeah, so as long as we are doing the prototype, we don't have any expectations that you have to split something. Yeah, so it's we who have to return back into the form that you think is the most appropriate for development.
Okay. Then let's say so in the tool you use. So you said that you use basically. So which compiler do you use? You use for the Fortran. Do you use the CUDA Fortran?
PGI CUDA Fortran.
Okay.
Plus an Nvidia toolkit, Nvidia CUDA compiler.
Okay. So basically, we would need to buy the PGI CUDA Fortran. This is in order to maintain and to compile. So this would be okay.
Yeah, that's true. As far as I know, they currently have academic licenses that are no cost, I think, if you are an academic organization.
Okay, so this we have to see. I don't know, EPFL, for instance, is for sure an academic organization. CERN sometimes is not. It depends on the license.
I see.
Because, I mean, we are not a university like EPFL, but for certain software, this make a difference between being academic or not. But this is something that we can figure out. Okay, so then let's say on reproducibility, there was this problem of this fused multiplication and add. Yeah. I'm wondering if on the CPU side, I mean, for us it's important to have the same results from different platforms. Now, I don't know if recent CPU have this fused multiplication and add inside. So
yes, I'm afraid they're starting to appear. AMD Bulldozer, I think. For Intel Haswell, yes. They have different fashion of FMA instructions, but they definitely start to appear on the recent CPU generations.
Okay. Well, okay, so this anyway then can come in the future. And of course, then if you start with the PGI, we cannot target the AMD cards. That's the other, by definition, if you want. Or we will never be able to target AMD cards with this approach.
Well, it's a question. We cannot do OpenCL in Fortran anyways, right?
Yeah.
Yeah. So my only hope is that from perspective of LLVM, both Nvidia and AMD have their compilers based on LLVM. They just ship different backends. So at some point, maybe we can hope for this rerouting of Nvidia front-end to AMD backend. So technically that's possible. So it's but it's an open problem. Nobody is developing anything on this. Some time ago we had a student who was looking into this, who was exploring this possibility from this perspective of compiler hook we did. So actually he needs exactly the same tool. He needs to extract the intermediate representation from Nvidia compiler, then somehow to refit it, to refactor a little bit, and then submit it to the AMD to AMD backend. And this problem really seems to be tackable. because the only difference between AMD and Nvidia is nowadays the set of built-ins. So, for example, thread IDX for CUDA ends up in some particular name in assembly. Then for AMD it ends up with some different name. So it's question of Control L R replace all instances of this. So to some extent, of course, not that much simple, but in general, this is the thing that could be done. Very fortunately, recent AMD architectures are no difference with Nvidia. So same fashion of multiprocessors. Again, just different terms. So wavefront instead of warp, and the hardware, the nature of the runtime is the same. So I would be rather optimistic about the possibility of inclusion in AMD target as well.
Which level? For instance, I don't know. The Nvidia can target. I mean, the Nvidia cards can run OpenCL, no? So
yes, they can.
Well, this particular pipeline is not involving OpenCL.
Yeah.
Because in CUDA Fortran, we don't have OpenCL Fortran.
Okay.
We don't even have a design for OpenCL Fortran, so it has to be invented before being implemented, right? So I'm talking more about the possibility to rewrite the output from Nvidia compiler to be an input for AMD backend.
Okay. I don't know. For instance, if you would follow the approach of GCC with the Dragon Egg and going to LLVM, and then I mean from there you can you target OpenCL from this up?
Again, why do you need OpenCL? OpenCL is high-level language.
Yeah.
So we are stuck with Fortran, right? We would probably not want to.
At least the final, let's say the final final OpenCL.
Well,
I don't know if there is some bytecode that
from LLVM you produce either PTX assembly or AMD IL assembly just directly without OpenCL.
Okay. No, I see now. Okay. Yeah.
Yeah. So it's simpler actually, and that pipeline involving Dragon Egg you mentioned, it actually enables to create an alternative implementation of CUDA Fortran, technically again.
Okay, I see. Okay.
Can you maybe put a number on the effort you spent to convert this code to be GPU compatible? Like maybe in comparison with a full re-implementation.
Well, what number shall we put for full re-implementation?
1.
1. 1. Well.
I'm interested in this question as well. So for the full implementation, of course, you need experts that rewrite the code. So which is a different resource, if you want. It's not only, let's say, programmers, but really domain experts that have to review everything. So this cannot be compared with, let's say, an effort of just, let's say, or using, let's say, a compiler or language technology to translate.
Okay.
I think it's interesting from him to know. I mean, how much maybe you would think after you, let's say, develop all these tools to transform a similar code. So how much, let's say, you need from a domain expert, and how much you need from let's say, computer scientist or.
Okay.
So I don't know if this is yeah.
So we were doing kind of sprints. So we prefer to concentrate on a single project for several weeks. And so in this term, I would estimate that that's not more than, well, 2 man-months. 2 man-months. So 1 month work of 2 engineers, fully dedicated. We are slower because we have a lot of projects still to be done in parallel. But this road itself is, we strongly believe it's a lot shorter than manual refactoring. You have seen this case of Cosmo model developed by Meteoswiss. I think, well, one of the best software engineers in Switzerland are involved in this project. At least 10 of them. And their project is going from 2012 or even 2011. And the results were just recently announced. So this is the amount of work to expect from manual code rewrite. And even that would be not complete code rewrite. They're doing complete rewrite only for Dynamics core.
Just so I can imagine better how to translate this. How well did you know the code before? Or did you know the code before? And well,
Code of Sixtrack, you mean?
Yes. And did you touch everything? You had to touch everything, basically.
Yes. Yeah.
Yeah. Did you know Sixtrack before? Like before you started this project, or did you know the code base well?
No, Igor introduced us not earlier than that.
It's completely fresh from zero to what you see. There was no prior history to handling Sixtrack at all.
But also, I mean, maybe we have to think also there is no particular knowledge, in my opinion, there is no particular knowledge required on the code, because in the end, what it makes the validation is comparing to the classical Fortran code running and then making, like we are doing, I mean, like it is done with Boeing. I mean, through Boeing, there is indirect validation of the results by having several computers, several platforms, several OS running the same code. And GPUs in this sense is like yet another platform. So even if it would have been a mistake, for instance, in making the porting of the code, it would show easily, you correct me if I am wrong, it would show easily in the generation, in the simulations which are created by the porting. And that would give a sign that it has been done wrongly or something, no?
Yeah, I fully agree. I mean, your approach seems a black box approach that is very solid. So, and also you don't need to understand each line of codes to see, or the memory structure to see really what is doing. I think, I mean, I can comment. It seems a very fast path. For instance, to let's say completely refactor the code, I would anyways need many months even to write the documentation and to recover all the know-how behind all the routines that are behind.
Mm-hmm.
So I think from this point of view, it's
yeah.
I think it makes sense to try at least. I mean, I see that there is a huge deal of technology behind and on the compiler side.
Yeah, so our intent is to develop the set of tools that would be universally useful for the same kind of software, and to document and explain these tools.
I think that the least we could do is just thank Dimitri and also, I mean, the team at Applied Parallel Computing, Igor, and also the Sixtrack team, which Ricardo is here representing it. So thank you very much for this interesting presentation, and I hope that, I don't know all of you, so maybe some of you are potentially interested in using this for your own coding. I assume that it's not everybody involved in the Beams department, or with Sixtrack, or both. But anyhow, since all this material, I guess you will offer us a copy of the slides?
Of course.
As well. So all this material will be available to you all, and if you have colleagues who have expressed interest or with which you want to share, it will be openly available in the seminar's website. Yeah. So thank you very much, Dimitri.